Good evening. I'm Dr. Sani Grace from Department of Pharmaceutical Analysis. The topic which we are going to discuss today is infrared spectroscopy from B Pharmacy 6th semester, and the subject is instrumental method of analysis. Now let's get into the introduction of the topic. So coming to the introduction, if you see here, IR spectroscopy. What is IR spectroscopy? IR stands for infrared. That is, the spectroscopy is the study of the interaction of electromagnetic radiations with matter. If we see the electromagnetic radiation, this is the electromagnetic spectrum which you are seeing here, which is made up of 7 different types of waves. That is radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and gamma rays. Coming to the infrared rays, they fall in between the microwaves and visible region. So these are the rays which we are going to study here. So from the EMR, that is electromagnetic radiations, infrared is the radiation which is going to interact with the atoms present in the molecules. So here if we see infrared spectroscopy is something that deals with the atoms in the molecules. So it is also known as atomic spectroscopy. And what we do here, the interaction, what happens here is, there are two types, right? Absorption and emission. Here, when the infrared radiation is absorbed, then a spectra is recorded or a peak is recorded. So that is the reason what we are trying to say about the infrared spectroscopy is, it is the study of interaction of infrared radiation which results in the vibrational transition. So here, as atoms are involved, atoms are always in vibration. They keep on moving. So they keep moving, right? They are in some kind of motion, rotational motion and vibrational motion. So basically, we are talking about the vibrations of the atoms. So with the central atom in a molecule, what happens is one atom is connected to two atoms with the help of a bond. And these bonds are present as springs. So whenever an energy comes and hits the molecule, they start vibrating, or generally they have a natural frequency with which they vibrate. Okay, so because of which they undergo vibrational transitions. If you see UV visible spectroscopy, we have dealt with about the electronic transitions there. But coming to IR spectroscopy, it deals with the vibrational transitions here. So the vibrations which takes place within the atoms is responsible for the absorption of IR spectrum, in which we will be studying. That is, the topic is known as infrared spectroscopy. Okay, mainly it is used in the structural elucidation to determine the functional groups. So what are the functional groups that are present within the molecule? You will be determining using the IR spectroscopy. We have already seen this point, that is, this IR region is present between the visible and microwave region. So here the energy will be, for any molecule, energy will be exhibited in three forms, that is electronic energy, vibrational energy, and rotational energy. Generally here we will, in this IR, we will not be talking about the electronic transitions. Mostly we are concentrating on the vibrational and rotational energies. Coming to the IR spectrum, any molecule which should exhibit IR spectroscopy should have two criteria. That is, the first one is it should have its own frequency. Okay, some frequency should be there for an atom to move or to have a movement or motion, right? That is the first criteria. And the second one is dipole moment. These two are the very important criteria required for the molecule to exhibit an IR spectra. Otherwise, we say that the molecule is IR inactive. Coming to the infrared spectrum, this is broadly, IR is broadly classified into three regions. That is near IR, middle IR, and far IR. So if you see any, and this here we are denoting in wave numbers and wavelength. So if you observe carefully here, in the IR, we are seeing about the wave numbers. So if you go to the energy equation, E is equal to hc by lambda. In that, lambda is the wavelength. So you get to know about here is energy is inversely proportional to the wavelength. And what is wave number? Wave number is the inverse of wavelength. So energy and wave numbers are directly proportional to each other. That is one point you have to remember. And any spectra, if you observe, you will be taking absorbance on the y-axis and wavelength on the x-axis, right? So coming to IR spectra, what happens is on the x-axis, you will be taking the wave number, and on y-axis, you will be taking the percentage transmittance. So because of which, instead of peaks, you will be observing dips in the IR spectra. That is one reason. So whenever you see IR spectra, that will be looking like an inverted spectra. That is the reason, because we are taking wave number on the x-axis. Okay, so here we are having three different regions near IR. It ranges from 14,000 to 4,000 centimeter inverse, and in wavelength it is 0.8 to 2.5. And coming to the middle IR region, we are having wave number from 4,000 to 400, and wavelength is 2.5 to 25. So this is the most important region, middle IR region, which is again subdivided into two regions, that is group frequency region and functional group region. And the group frequency region ranges from 4,000 to 2,000 centimeter inverse, where you will be knowing about the aliphatic nature or unsaturation if it is present, what is the arrangement of the CH bonds that is present in our molecule. You will get to know about that. That is the reason why it is known as group frequency region. And coming to the other region, that is from 2000 to 400 centimeter inverse, it is called as functional group or fingerprint region, where almost all the functional groups that are present in a molecule can be identified. That is why they are known as fingerprint region. For example, 1720 centimeter inverse is for ketones, and 1725 is for aldehydes. Like that, you will get to know about the each and every functional group's wave numbers in this IR spectra in this particular region, that is the fingerprint region. And no IR spectra of any two molecules will be the same except the optical isomers, where you will be finding similar kind of stretchings, right? Because of that, there is a possibility that you might be finding for the isomers, but actually fingerprint is something which is not unmatchable, or it is very specific for each and every organic molecule. And then the next region is far IR region. Far IR region ranges from 400 to 10 centimeter inverse, and in the wavelength it is 25 to 1000 micrometer, which is almost this region will not be studying more in our pharmaceutical. Pharmaceutically, the most important region is the middle IR region, and that too functional group region. Next, coming to the principle of IR spectroscopy. So in the IR spectroscopy, we have seen, see, these are the two atoms of a molecule, and in between, the bonds are in a form of springs. They are attached in the form of a spring. So what is this? The study of interaction of electromagnetic radiation with vibrational and rotational frequencies within a molecular structure. Vibrational and rotational references within a molecular structure is termed as IR spectroscopy. So we have seen here in this, the electromagnetic radiation, especially we will be studying about the vibrational and rotational frequencies. Okay, then whenever an energy in the form of infrared region is applied, then it causes the vibration between the atoms of the molecules. So here the main principle of IR spectroscopy is, to the atoms, in between the atoms, we will be having a bond in a form of a spring. So they will be moving with a certain frequency, or it is also known as natural frequency of that particular atom. So when an IR radiation come and hit this bond, what happens? Whenever the IR frequency is equivalent to the applied frequency is equivalent to the natural frequency of that particular atom, the IR spectra will be absorbed and peak, you will be able to see the peak. So that is the major principle. See, whenever an IR frequency is equivalent to the natural frequency of the vibration, absorption of IR radiation takes place. So a peak is observed, and from the peak, you will be able to determine what is the functional group or what is the bond that is present in that particular molecule. So IR spectrum of a chemical substance is a fingerprint of a molecule for its identification. So basically for structural illustration, you will be using IR spectroscopy. Now coming to the vibrations, as molecular vibrations, we have already seen that vibrations are very important, the requirement for an atom to be IR active, right? So we are having two different types of molecular vibrations, stretching and bending vibrations. Out of these two vibrations, stretching vibrations require higher energy, or they are observed at the higher wave number compared to that of bending vibrations. So in the stretching vibrations, the whenever you are considering the molecular vibrations, the two parameters which you have to keep in your mind are about the bond length and bond angle. So coming to the stretching vibrations, the difference will take place in the bond length, and bond angle will not change. All those vibrations comes under stretching vibrations, and they are again subdivided into two types, that is symmetrical and asymmetrical. And whenever I say bending vibrations, so here there will be a change in the bond angle and bond length will remain same. These are again subdivided into two types, that is in plane and out of plane. In plane we are having scissoring and rocking, and out of plane we are having wagging and twisting. So let's see how the molecules will vibrate here. So in the stretching vibrations, if you see, if this is the central atom and these two are the atoms which are joined to the central atom. In the symmetrical stretching, what happens is, from the central atom, the two atoms which are connected to the central atom will either come near or go away, move closer or move away from the central atom. So there will be a change in the bond length, but not in the bond angle, like this. So this is called as symmetrical stretching. When you say asymmetrical stretching, to the central atom, either one of it will be coming closer and one will be moving away. So like this, if you see, without a change in the bond angle, then it is called as asymmetrical stretching. So these are the two types of stretching vibrations. Coming to the bending vibrations, here what happens is, there will be change in the bond angle, but no change in the bond length. If this is the bond length, there will be no change in the bond length. Coming to the scissoring, either the two will be coming close or will be moving away, like this. This is called scissoring vibration. And coming to the rocking, they will be moving in a either that way or this way, without the change in the bond angle. So this is in plane. Now coming to the out of plane, if you see in the out of plane, we are having twisting. Twisting is something like this. Instead of going in one plane, they will be going in one plane. And wagging, two will be moving forward and backward. So these are the different types of vibrations, molecular vibrations you will be observing. And based upon those stretching and bending, all the spectra, you will be able to interpret the spectra easily if you get to know about, like, whether symmetrical stretching is taking place or asymmetrical stretching is taking place, or any bending or deformation. Bending vibrations are also called as deformation vibration, because you are changing the structure of you are forcing the molecule to change its structure, right? So that is why it is also known as deforming vibration. Now let's see the instrumentation part of the IR spectroscopy. Generally, basically, we are having two types of infrared spectrophotometer. They are characterized by the manner in which the infrared frequencies are handled. So here we are having two types, that is dispersive instruments and Fourier transfer IR instrument or infrared instrument. Why you call dispersive instruments here is, here whenever the infrared light is coming out of the sample, it is characterized by dispersion. That is why into individual frequencies, the infrared will be having different frequencies. It will be separated into individual frequencies by the principle known as dispersion. That is using either prism or grating monochromator. Those instruments come under dispersive instrument. When I say Fourier transform infrared instruments, in this what happens is, you will be having the whatever infrared frequencies that are coming out of the sample, they are allowed to interact and produce an interference pattern that can be either constructive or destructive interference, and this pattern is then analyzed mathematically using Fourier transform to determine the individual frequencies and their intensities. So here we will see in detail about these instruments. So these are the dispersive spectrophotometers. In this dispersive spectrophotometers, we are having single beam and double beam. In the single beam, what happens is, so actually in the IR spectrophotometer, the sample will be immediately after the source here. So from the source directly, the IR radiations will go into the sample, and a part of it will be absorbed by the sample, and the remaining is transmitted. So as we discussed in the previous section earlier, that is, we will be measuring percentage transmittance in the IR spectra. So the amount of light that is transmitted, that gets out of this entrance rate. And with the help of the dispersion device, it can be either prism or a grating monochromator that will select the desired wavelength, and then it will send that particular wavelength out of the exit slit, and that will fall on the detector, and we will be converting it to the wave number, and then that will be generated or recorded as IR spectra in the single beam. So here from the source only one beam is coming to and will enter the sample. That is the reason why we call it as single beam spectrophotometer. Now let's see double beam spectrophotometer. What happens in double is, this is the infrared source, and from the infrared source equal intensities of light get split and they fall on the mirrors. Whatever blue objects you are seeing here are the mirrors. They fall on the mirrors, and one beam will get into the reference cell and the other beam will get into the sample cell, and with the help of the mirrors they will come and fall on this rotating mirror. So here you will have a rotating mirror. On the half rotation, up one part is covered and the other part act as a mirror. So whenever, what happens here is, when it is in the half rotation, one time if it opens to the sample, for the reference it is closed. In the either way, if it is open to the reference sample, it is reference cell, it is closer to the sample cell. So we'll start with the sample cell. So it will come here, and we are expecting that our rotating mirror is taking the light that is transmitted from this mirror, and then it will go into the prism. So a prism or a diffraction grating, you can call it as any grating or prism, they act for the monochromator. They will help us for selecting the desired wavelength to fall on the detector. That's it. So here you will be taking a prism, and they will go through the prism here, and finally from the lithomirror they will get into the infrared detector. So in the same way, now what happens in the second half rotation, that will be close to the sample cell, and the second beam which is coming from the reference cell comes and fall on the mirror, and then it will pass through the prism and then finally reach the detector. So here and will be recorded in the chart recorder with the help of chart recorder. So this is the double beam. So two beams. So at a time we can measure only one cell, that is sample as well, or a reference cell. So simultaneously you can measure reference as well as sample cell. So this is most widely used or recommended kind of thing. It not only for IR, but you can also in the UV spectrophotometer also the double beam works in the same way. But coming to the UV, there you will be having sample cell after the monochromatous, okay, monochromating system. But coming to the IR, you will be having sample before the monochromatings. That is the major difference. And then this is about the double beam spectrophotometer. Now let's see Fourier transform infrared system. In the Fourier transform infrared system, it is almost similar to that of the what you call single beam as well as double beam spectrophotometer. But one part which is in what you call add in this FTIR system is this interferometer. If you see here, this is the interferometer. In the interferometer, what happens? You have this whole dotted box which you are seeing, dotted rectangle box you are seeing here, right? That is the interferometer. In that interferometer, what happens is you will be having a beam splitter which is placed like at 90 degrees to it. So along with it, you will be having a moving mirror here, fixed mirror, and also concave mirror also will be there. And here actually for the from the beam splitter to reach to the moving mirror, the whatever IR source is there, IR source will be coming into this interferometer. Once it comes to the interferometer, it will fall on the beam splitter. Then this beam will split the IR radiation equally to both sides, that is to the fixed mirror as well as towards the beam splitter. To reach the beam splitter, it will take a longer curvature. Here you are not able to see, but actually what happens is from the beam splitter to reach to the moving mirror, it will take a little bit longer time compared to the fixed mirror. So once with the help of interferogram, what happens this with the help of this interferometer, the radiation which is transmitted out of this will come here, will come out of the fixed mirror and reach to the concave mirror here, and then this moving mirror, it will reach the moving mirror. So from moving mirror and fixed mirror, you will be getting one beam that is known as recombinant beam. or it is also known as interferogram, where your light has been traveled for a longer distance. That is, IR radiation will be traveling for the longer distance, and then it will come and fall onto the sample. Okay, and here you are seeing a laser or laser which is connected to the moving mirror, which will be helping us to control the speed of the moving mirror. Accordingly, it will be recombining the beams from the fixed mirror and the moving mirror, and then finally that recombined beam will reach the detector, which will help us in the better analysis of the sample. Then finally the transmitted sample will be reaching to the detector. So what is Fourier transform is, it is nothing but calculation part. So if you generally see the waves, okay, frequency to time domain you will be converting. So generally if you see the spectra, it looks very complex directly if you are not converting. But coming to the Fourier transform, what happens is you will be able to observe a more clear spectra compared to the normal conventional spectra. So that is the reason why we choose this FTIR spectra. So the required spectra, whichever we need for the structural illustration, only that part can be highlighted, and that the required peaks, because all peaks are not required in the IR spectra, right? So if you use Fourier transform, only the peaks which are required, that can be easily interpreted using this. That is the major difference between the normal dispersive IR spectrophotometers and FTIR spectrophotometers. So coming to the block diagram of IR spectrophotometer, as we have already seen in the different types of spectrophotometer, that is, from the IR source, the light will be reflected to the sample, and once the sample light IR light is reflected to the sample, so whenever that applied frequency will be equivalent to the vibration of that molecule, that will be absorbed and the remaining will be transmitted. The transmitted radiation will come and fall on the detector and finally to the recorded system. Now let's check out the instrumentation parts one by one in the IR spectrophotometer. So the first one is the sources. In the sources, the most widely used sources is the Nernst Glover source. It is a combination of oxides of zirconium, erbium, yttrium, usually like diameter of 2 mm and length of 30 mm. So this generally looks like our conventional household bulb. So it is a generally it is non-conducting at the room temperature. That is the reason why heating is required to bring it to the temperature of about 1000 to 1800 degrees Celsius. And next source is the glow bar source. In the glow bar source, it is actually made up of silicon carbide rod. Okay, and it is usually diameter of 4 mm and length of 50 mm. For this also heating is required to produce IR radiation. The heating is required up to 1300 to 1700 degrees Celsius. So in the whatever power consumption is there, it is generally higher than the Nernst Glover for the glow bar source. So water cooling system is also required to cool the metallic rods, that is the silicon carbide rod, metallic rod electrodes which are attached to the rod. Okay. And the next source is incandescent lamp. Coming to the incandescent lamp, it is a tightly wound nichrome coil which is heated to about 100 degrees Celsius by electric current. And this this also has a black film oxide is formed on the coil, giving what you call, for more emission of the IR radiation, you will be having this black film oxide. It has a longer life than the Nernst and glow bar source. Then the next one is the mercury arc, generally used for the far IR regions where the frequency, where the wave numbers are less than 200 centimeter inverse, and it is a high pressure mercury arc which consists of quartz jacketed tube containing mercury vapor at pressure greater than 1 atmosphere. So whenever a current passes through this lamp, the mercury will get vaporized, excited and ionized, okay, which forms a plasma discharge at high pressure. That will be acting as a source of IR radiation. So these are the different sources of IR. Next, coming to the sample handling. So in the sample handling here, in the IR spectroscopy, all the types of samples you can analyze, that is solids, liquids and gases. So another difference of UV and IR is the samples. In the UV, we can only use the solutions, but coming to the IR, you can use solid, liquid as well as gas samples for analysis. Okay, sampling. So IR spectroscopy deals with the measurement of IR spectra. It is used for the characterization of solid, liquid, and gas samples, and whatever material which we are using for the sample handling should be transparent to the IR region, throughout the IR region. So generally we'll be using NaCl, that is sodium chloride, potassium bromide, or thorium bromide. These kind of materials you will be using for sample handling. So let's see with the sampling of solids. So generally sampling of solids consists of four different techniques. The first one is solid film technique, pressed pellet technique, and mull technique. The other technique we will see in the last one. For the liquid samples also we will be using in the same way. So I have included that in the next part. Okay. So sampling of the solids. So we'll see about the solid film technique, pressed pellet technique, and mull technique. In solid film technique, what happens is you have to take the solid sample and you have to mix it in the volatile solvent. Then you have to apply a drop of it onto the film, onto the flat surface of the flat. So I have told you, you will be taking sampling NaCl or KBr or thorium bromide. You will be using that cells only. Okay. So you have to take either of the plate and then you have to place a drop of that sample solution which you have prepared. That is, the sample is mixed in a volatile solvent and you will place a drop of it on that plate. Then you will allow it the solvent to vaporize. Because it's volatile, obviously it will vaporize after some time. Once it vaporizes, it forms a thin film on the solid plate which you have taken. Now you will pass the IR radiation onto this sample and then it will go for the detection. Okay, that is how you will be doing with the solid film technique. And the next one is pressed pellet technique. So here in the pressed pellet technique, this is the hydraulic press. If you see the diagram, this is the hydraulic press. Okay, you will have one disc unit, a circular disc you will be having. In that you have to take the solid sample. How? One part is to 100 parts. That is, one part of the sample you have to mix with the one part of the sample you have to mix with the 100 parts of KBr. You have to nicely grind it in the mortar and pestle properly, and then you have to take the whatever disc you will be having, a disc. Into that disc you have to fill the powder. Okay, after filling the powder you have to place it here. Then slowly you have to press it down. Then you, with the help of this pump, hand pump, what happens is you have to adjust the pressure. Once you get the appropriate pressure, you have to really see. You have to, once the disc is placed, you have to take the sample in the disc. Okay. Then you have to place the disc here. Then you have to close this pump you're seeing here, right? This one you have to, this piston kind of thing, that hand piston kind of thing, you have to touch it to the disc holder wherever you have placed the sample. Now you have to release this. After releasing this, you have to close, you have to tight this. Now with the help of this hand pump, you have to pull it down for adjusting the pressure. Once the desired pressure is being created, you have to release this handle and release this, knob, adjustment knob here. What happens then? This also you have to turn up. Take out the disc, you will get a pellet. That is the sample pellet you will get. Directly you can take the pellet and you can see it in the infrared spectroscopy. That sample you can place and go with the IR radiation. So in this technique, a small amount of finely ground solid sample is mixed with the 0.1 or 2% weight of the dry powdered KBr or NaCl, and it is compressed. Just now we have seen. So the mixture is compressed under very high pressure for about 10,000 to 15,000 pounds per square inch, to yield a transparent disc about 1 centimeter in a diameter and 1 to 2 mm thick. So this is the size of our disc which we are going to prepare. That is the sample disc. And this disc is prepared in vacuum to eliminate air or moisture. Because we know KBr is hygroscopic in nature, you have to make sure immediately after preparing, the sample should be analyzed. These pellets are transparent to IR region and it is used for the analysis. So this is the second technique. Coming to the third technique, mull technique or Newton mull technique, you can call it as. It is mineral oil. The solid sample, whichever is there, you will be mixing it with the Newton mull or mineral oil. You will make it into a thick paste in a mortar and pestle, and then you will apply it to the plates, that is NaCl or KBr plates, like a thin film. Once you are applying it, then you will be mounting it on the path of the IR beam and the spectrum is recorded. That is what happens with this News-Jornal technique. But one of the disadvantage of this News-Jornal, not disadvantage, one of the thing which you will observe is you will be observing absorptions at different wave numbers, like 4 wave numbers you will be observing with this mineral News-Jornal, because it itself has that absorption at that particular 4 wavelengths because of this CH stretching and CH bendings. Okay, so to avoid that or to shift the wavelengths of that particular stretching and bending vibrations, what we do is we will be preparing it by mixing in hexachlorobutadiene or chlorofluorocarbon oils. So along with this News-Jornal, you will be adding generally hexachlorobutadiene, so that you will not be able to observe this CH stretching and CH deformation, which will be interfering with that of mostly with the carbonyl compounds. So just to avoid that, we will be using this hexachlorobutadiene. So these are the 3 different techniques of solid sampling techniques. And now coming to the sampling of liquids. Coming to the sampling of liquids, here what we will do is, you have to make it normal running solution only. These liquids are usually examined as a thin film sandwiched between the 2 polished plates. So you will be taking 2 plates with very less space between those 2 plates, and then you will be pouring the liquid sample solution, which will appear like a thin film. Okay, so aqueous solvents cannot be used because they cannot dissolve alkali halide. So organic solvents like chloroform are generally used. Then the sample thickness should be 0.01 to 0.1 mm to give the transmittance between 15 to 70%. So these are the things which we have to remember. And some salt plates are highly soluble in water. So that is the reason what we have to do. Generally, the washing also will not be done with water. So you will be taking like toluene or chloroform for washing the sample cells, because they will not dissolve and they will be reacting with the salts will be reacting with the aqueous solution. So generally, when you are handling IR samples, you will be using organic solvents like chloroform, CCF, carbon tetrachloride, like that, etc. And the next one is sampling of gases. Coming to the sampling of gases, in the sampling of gases, you will be having one evacuated cylindrical cell, that is which has IR transparent windows. So you will have a gas sample with inner lining with a metal lining you will be having. Because of which whenever the sample is in the form of what you call gas, right? So it is with sample is in the form of a gas, and within that you will be having IR transparent windows, so that they are made up of again KBr or NaCl plates. So once and it also has whatever the gas sampling unit is there, right? In that you will be having mirrors. That mirrors will help us in reflecting the radiation that is falling from to the sample, right? You will, so that more kind of emission or more it is reflected back. Multiple reflections is possible in this gaseous in the sampling of gases, which will help us to determine the gas sample. That is what we are trying to say here. So the gas must not react with the cell windows or the reflecting surfaces. So inside you will be having the reflecting surfaces. That is what we are discussed now. So the gas analysis are performed with IR, but the method is not commonly used because of the lack of sensitivity. The moisture must be avoided. In addition, the windows and other instrument components which are constructed of soluble salts may be damaged. So that is the reason. Generally, we have seen in the liquids also, water, aqueous solvents or moisture must be avoided because they will damage the moisture will damage the sample holders. Then the solution sampling technique, or it is also known as running solution sampling technique. So here what we do is we'll take the solid sample and you will mix it in a suitable solvent, and then you will be pouring this liquid solution into the sample holder, and then you will be able to analyze the samples in solutions. And the absorption due to solvent has to be compensated, and whatever solvents we are using, that should not show any kind of absorbance whenever it is mixing with the sample. Okay, so for that reason, we will be using different solvents like carbon tetrachloride, carbon disulfide, or chloroform. These all are transparent to the IR region. So that is the reason why we will be using this as the solvents, not water. Water will not be used as solvents. Okay, so these are all the different sampling techniques for how you will handle the samples. That is solids. It can be either solids, liquids, or gases in IR spectra. Next, coming to the monochromatic system. So first we have seen the sources, four different sources we have seen: Nernst Glover, then Globar source, then incandescent lamp, mercury arc lamp. Then the next part we have seen is sample handling. Because after the source, the IR radiation will directly come and hit the sample only. And that samples how you will go for the sampling for solids, liquids, gases, we have seen. And now after that, they will absorb the part of IR radiation and the remaining will be transmitted. So the transmittance rate should be from 15% to 70%. That should be our criteria. So whatever IR is transmitted, from that we will get to know the what is the molecule or what is the bond that is present in that particular organic molecule. Okay, so the next one is selection of the wavelength. Okay, for the selection of wavelength, what we are going to use is monochromators. So in the monochromators, generally we will be using two different types of monochromators, that is prisms and gratings. So here, see, to select the radiation of any desired frequency from the source and eliminate other frequencies, you will go for the monochromators. And this consists of monochromator which has the dispersion element and slit system. Not only dispersion element, if it is dispersion, it is called as prism. In gratings, we have different principle, right? Diffraction and transmission. So let's see one by one. So this is the prism chromator. In the prism chromators, we are having two types, that is single pass and double pass monochromator. In this diagram, you are not able to see the sample solution here. So once from the radiation source, when your IR light is being transmitted from the incandescent lamp, what happens here? It falls on the first, they will reach the sample solution, and from the sample solution, the transmitted light comes out of this entrance slit and then fall on this condensing mirror, which is reflected back to the prism here. And this prism actually where the dispersion takes place, and then from here litro mirror, it gets reflected back. Once it is getting reflected, only the selected wavelength, the desired frequency, comes out of the exit slit. So this is single pass monochromator, where only once one radiation or one time it is passing through the prism. See, one time it is passing through the prism and then it is reflected back. Whenever it is coming, whenever it is passing two times from the prism, that is, it is incident as well as reflected two times, the dispersion is taking place, then you will call it as double pass monochromator. That is the only difference. So here if you see four lines, 1, 2, 3, 4. So the same way here from the entrance slit, so from the radiation source it goes into the sample, and then from the sample IR light will be transmitted through the mirror, which will reach to the prism where the dispersion will take place, and with the help of litro mirror it is reflected back to the condensing mirror. So here with the help of a plane mirror, arrangement of this plane mirror will help us for the double pass. So this is the double pass. Like this, it comes out of the exit slit. So by arranging this, the more amount of what you call reflection takes place, the selection of frequency will be that same selective. So that is the reason why I will go for the double pass monochromator. So the desired frequency will come out of this exit slit and will fall on the detector directly where it is getting detected. So in the prism monochromators, the principle is based upon the dispersion of the IR light. Coming to the grating monochromators, what happens here? We are having, see, the same way here also you will be having slits. This is the source and you have a sample. From there, it is the entrance slit. These are the mirrors and this is the grating. So grating is generally of two types, that is transmission and diffraction. Based upon the diffraction pattern and transmission pattern, our selection of the wavelength will be taking place in this monochromator system. From the exit slit, the desired frequency or desired wavelength will be coming out of this exit slit, that is F. Okay. So this is about the monochromators. Now coming to the detectors. So in the detectors, we are having different types of detectors. First one is thermocouple. In the thermocouple, this is made up of two different semiconductor materials. Obviously, the two different semiconductor materials, they will have two different kinds of temperature. Generally, whenever your IR radiation comes and fall on one semiconducting materials, it will create a potential difference between those two materials, right? So whatever potential difference it is creating, that will cause the current to flow through it. And the amount of current which is generated is directly proportional to the intensity of the light that is falling on the detector or on this thermocouple. And this thermocouple is closed and evacuated steel casing with KBR window, okay, to avoid the loss of energy by convection. So this is about the thermocouple. And the response time of thermocouple is 60 millisecond. And to enhance the sensitivity of thermopile, we will pile up the different, several thermocouples are connected in a series. So to give the better results, and that kind of detector is known as thermopile detector. And the next one is bolometer. In the bolometer, it is based upon the Wheatstone bridge principle. Here, if you see, this is the Wheatstone bridge, where the four frequencies, whatever here you are seeing resistance here, right? These are the resistors. These four resistors must be equal. Then only this galvanometer will be showing 0 as a reading. So our main thing, this is also known as null detector technique. So here, whenever IR radiation falls on the resistor or the indicated, so these two are the platinum strips. They are made up of the platinum strips. Okay, so whenever the IR radiation come and falls on this platinum strip, what happens? Obviously, it will create a deflection in this galvanometer. To balance this, you will be arranging the to balance this galvanometer to 0, you have to use some kind of resistance over this, right? For getting this galvanometer reading as 0. So for that reason, what you will be doing here, uh, whatever adjustment you are doing for making the galvanometer as reading as 0, that is directly proportional to the amount of light that is falling on the detector or the intensity of the radiation that is falling on the detector. The response time for this is 4 millisecond. So if you see, this is having lesser response time compared to that of your thermocouple, right? So if you see here, it is based on bolometer, it is based on the Wheatstone bridge principle. For every 1 degree rise in temperature, electrical resistance of metal increases. So it depends upon the intensity of the radiation, how much temperature will be increased. Okay, for every 1 degree rise, you will be seeing that the electrical resistance of that particular metal also increases. So a bolometer usually consists of a thin metal conductor made up of platinum strips coated with lamp black. That is what we have discussed here. So this is the bolometer, okay, where IR radiation, you are letting the IR radiation to fall on it. And the amount of current flowing through the galvanometer measures the intensity of the radiation falling on the detector, and the response time is 4 millisecond. You have seen this, right? So the next one is pyroelectric detectors. What is pyroelectric detectors? Means they themselves do not produce any electricity, but whenever they are heated, pyro means thermal energy, or you are heating it, so it will produce electricity. So for that purpose, all the detectors which require heating to produce current comes under the pyroelectric detector. So when IR radiation are falling on the detector, for heating up you require one metals pyroelectric crystals. See, for that we are using these pyroelectric crystals like barium titanate, lead zirconate, triglycerin sulfate, etc. So it consists of a thin plate of pyroelectric crystal of 0.25 to 12 mm in size. So this crystal is placed between the two electrodes, which is connected to an external electric circuit. So whenever the crystal is exposed to the IR radiation, it will absorb the heat, leading to the change in the dipole moment, and where you can directly read the intensity of the radiation falling on it from the spectra recorded. Okay, and the response time is 10 millisecond. So we have seen, this is all about the instrumentation of the IR spectroscopy, where we have discussed till about monochromators. Then we have seen the detectors, all the different types of detectors like bolometer, thermocouple, and pyroelectric detectors. Okay. Now let's see the factors affecting the vibrational frequencies. Generally, we are having these five factors, that is vibrational coupling, hydrogen bonding, electronic effect, bond angles, and resonance. What is vibrational coupling is, so actually if you see CH bond, CH2, for example, you have a molecule with CH bond. So we will be expecting only one stretching for that particular, because it will be having the same vibrational frequency, right? But what happens here is you will be observing two stretchings. One will be symmetrical and the other one will be asymmetrical. Why? Because of the coupling. So whenever a vibration coupling happens between CH vibration groups, the vibrations will be occurring at the higher frequencies than compared to that of to higher frequencies. So in the stretching also, we are having two types of vibrations, right? Symmetric and asymmetric. Symmetric generally will not have any kind of stretching because the dipole moment will not be more. Coming to the asymmetric, dipole moment will not be there. Coming to the asymmetric vibrations, what happened? They will occur at the higher vibrations. Okay. Then this kind of coupling, whenever you will observe the vibrations at a higher frequencies, that will come under the why you observe that kind of increase in the frequencies, because of this coupling only. And the next one is hydrogen bonding. Generally, whenever a groups like oxygen or nitrogen are present, hydrogen bonding is generally observed in that particular infrared spectra also. So when we use mostly organic work will involve relatively non-associating solvents, and more polar solvents such as acetone or benzene will certainly influence OH and NH absorption. So basically what we are trying to say is intermolecular hydrogen bonding and intramolecular hydrogen bonding are something which you will be observing. So whenever you see intermolecular observing, they will be giving rise to broad bands, and coming to the intramolecular hydrogen bonding, they will be giving a sharp and well-defined bands. And one more thing is concentration of the sample also will affect the hydrogen bonding. That is intermolecular hydrogen bonding on dilution, the bands will disappear, but intramolecular, it is not, it is unaffected, independent of the concentration. The other one is electronic effects. We have different electronic, because of electronic effects is nothing but because of the neighboring atoms that are present, that will affect the environment, leading to the differences or stretches, differences in the wavelengths or frequencies. That they are inductive effect, mesomeric effect, and field effect. So when I call inductive effect, for example, any alkyl group is present, what happens? It will be causing positive. Positive effect means positive inductive effect will go to the higher frequencies. Coming to the negative inductive effect, it will lead to the lower frequencies. And the mesomeric effect is because of the resonance, which we will see in the resonance. Then coming to the field effect also, that will be affecting the frequencies. Wave numbers will be changing. Then coming to the bond angles. So the CH vibration, so bond angles will generally, as the hybridization goes from sp3 to sp2 to sp1, though as the S character of the CH bond increases, the bond length will become shorter and the frequencies will rise. Okay, and the last parameter is the resonance. Coming to the resonance, whenever the resonance are there, in for example in carboxylic acids or in alcohols, what happens? It will increase the bond strength, and it will result in the increase in the absorption of the frequency. So in this way, resonance can affect the absorption of IR of CO stretching, that is CO bond. So these are all the different parameters which will be affecting the what you call vibrations or stretchings in the IR spectra. Then coming to the application, we'll just see the gist of applications of IR. It is used for the determination of molecular structure. We have already seen it is a fingerprint of a molecule. All the functional groups that are present can be easily be determined in the fingerprint region, and it is helpful in the determination of the molecular structure. In qualitative analysis of the functional groups, because of the fingerprint region, we will be able to analyze the functional groups. The next one is studying the progress of the reactions, detection of the impurity in the compound, and shape of symmetry of the molecule. And then with all this, and then presence of water in a molecule. If a water or moisture is present, you will be observing peak at 3000 centimeter inverse, which determines it contains moisture. Then the examination of old paintings and artifacts, and also identification of organic compound. So basically we can say that IR is used for the qualitative as well as quantitative determination of the organic molecules. So this is all about our IR infrared spectroscopy. I hope we have covered all the topics related, almost all the topics related in the IR spectroscopy, related to the introduction, principle, vibrations, and then instrumentation, and the different types of instruments that are involved in IR, and the reasons for this molecular stretching, and then the applications of IR. So if you want to get to know, and if you want to get to know more about the videos related to pharmacy related topics, and more in the our subjects in pharmacy, like instrumental method of analysis or pharmaceutical analysis, please subscribe to the Pragara channel, where you will get an enriching learning experience related to all pharmacy topics. Thank you for joining us in this seminar, on this webinar. Thank you.